All right, another video on the sampling distribution. What I really want to talk about in this video is the shape of the sampling distribution. And I know I already wrote here that it was normal, but I want to talk a little bit more about why it's normal and in what situations it'll end up being normal. When can we do these questions, essentially? But before I do, in the last video, I left you with a question. I made the observation that we kind of asking the same question in red and in blue. All right, what's the probability that this thing is greater than 20? What changed was this thing. Over here, it was one single pepperoni pizza that I was talking about. And I want to know what's the probability that one pepperoni pizza has more than 20 pepperonis on it. Whereas over here, it was the average of 5 pepperoni pizzas. I want to know what was the probability that if I grab 5 pepperoni pizzas, the average number of pepperonis on those pizzas is greater than 20. And that was significantly less than it was over here. And I claim that that makes sense. And you can see that that makes sense in two different ways. One way is you can go back to this applet and just kind of find 20. 20 somewhere about here because 16's in the middle and one standard deviation above the mean should be roughly at the inflection point. And one standard deviation of the mean is 21. So we're roughly in here. Here's where 20 is. If you look to the right of my mouse, there's a lot of area there. If you look to the right of my mouse down here, there's not very much. Right, this is roughly 20% to the right of my mouse. This is roughly 4% to the right of my mouse. You're like, all right, I guess, but does that make sense? Claim that it does. Because think about what it would mean in order to have the average number of pepperonis be greater than 20. It's going to be hard. You're going to need to get really lucky a lot of times, right? It's not even that frequent that I get a single pepperoni or a single pizza that has more than 20 pepperonis. Here I did. I got lucky, but it doesn't happen all the time. And when I do, I still have 4 more pizzas to average that out with. And those 4 pizzas probably don't have more than 20 pepperonis. I mean, one way you get the average to be more than 20 is if all 5 pizzas had more than 20 on them. But that's going to be super duper unlikely. You're probably going to have some that have less than 20, maybe less than 16. So that means if you're going to have some that have less, you're going to have some that need more in order for the average to be 20. It's pretty unlikely that the average will be greater than 20. That's why I claim that it makes some sense that the answer to the blue question is so much smaller than the answer to the green question. Anyways, what I want to talk about in this video is the shape of these distributions. What's going to happen in these problems, or what has happened in all the chapter 3 problems, is it's told you that the shape is normal. We can only do all this stuff if the shape is normal. We can only use the normal CDF function or the inverse norm function if the shape is normal. That wasn't a big deal in chapter 3 because in every single problem it said, hey, it's normal, don't worry about it, use your calculator functions, learn how to use them. In chapter 4, sometimes that happens, sometimes it doesn't. What I want to give you in this video are a couple different criteria for when the sampling distribution is normal. There's 2 different ways. The first one's a little bit easy. Normal, and then maybe I'll write either because, I'm going to give you 2 different ways. Either because the parent distribution is normal. And that's what we saw in the applet last time, right? When the parent distribution is normal, the sampling distribution ends up being normal like you saw here. And that kind of makes sense. If the number of pepperonis on a given pizza are symmetric and bell shape, then when I average them all out, it kind of makes sense that it would still be symmetric bell shape. But here's something that maybe is a little bit more surprising to you. I'm going to clear this all out. I'm going to change this distribution. Instead of making this normal, I'll make it skewed. Right skewed, I guess. And then I'm going to play the same game. I'm going to randomly select 5 pizzas. Right? I'd expect most of them to be over here because most of my observations in a right skewed distribution are over on the left. But I have this big long tail going out to the right, which makes it entirely possible that every once in a while I'll get an observation out here with tons of pepperonis on it. That's sort of the idea here. If we're assuming that pepperoni pizza is right skewed, then here's 5 pizzas, and here's the average of those 5. And I can do that again and again and again. And as you know, I'm amused by, whoa, got one way out here in the tail, watching these pizzas fall, and maybe you're less amused than I am. At any rate, I can figure out all these averages. If I click this 100,000 button, it's going to pick 500,000 pizzas, and it's going to make my distribution down here. And I would expect it to be a scrunched up version of this. Right? I'd expect the spread to be smaller because we talked about in previous videos, the spread of the sampling distribution is less than the spread of the parent distribution. because you could have one or two outliers or really strange results, but you still have, if we have 5 in each of these samples, 3 or 4 pizzas to average that out with to pull it in closer to the middle. So I'd expect it to be less spread out, but I don't know. I'd expect it to look like this because why not? But look what happens. Right, when you do this a bunch of times, you get this picture and you get something that is almost normally distributed. If you look really careful, if you're really picky, you might see a tiny tail out here to the right. I don't know. If somebody just gave me this as a histogram and they're like, what shape does it have? I'd probably be like, yeah, it's close enough to normal. But they might be like, actually, I was going for very, 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 very slightly right skewed. Almost normal, but with a little skew. Okay, fine. If you're being really picky, maybe you see a tiny bit of a skew here, but most of it's gone. That ends up being a really important fact in a statistics class. It's what's called the Central Limit Theorem. And what the Central Limit Theorem tells you is that even if the parent distribution is not normal, the sampling distribution wants to be normal. You're like, what the hell do you mean wants to be normal? Well, it turns out that the size of the distribution, if it's bigger, if I just have 2, if I make n equals 2, then what I'm doing is I'm grabbing 2 pizzas at a time. All right, there's 2, there's the average. Here's 2, here's the average of those 2. Here's 2, here's the average of those 2. And if I do this a bunch of times, I still see this tail here. But when my value of n gets larger and larger, we saw it at 5 already, but here it is again. Here's when my value of n is 10. Right, grabbing 10 pizzas at a time. Takes a little while now, and then figuring out the average. 10 pizzas at a time, wait a little while, figure out the average. Do that a whole bunch of times, and now you hardly see any skew at all, right? This looks really good. This is getting closer and closer to normal. If I make n larger and larger, my distribution becomes more and more normal. That's a really important fact. In fact, it's important enough that I'm going to write it in your notes. The sampling distribution will end up being normal in every problem you do in this class, because if it's not normal, I can't ask you to use the normal CDF function. So I have to contrive things. I have to make it work out so that it's normal. But not only am I going to ask you what the shape is, I'm going to ask you why. So you're going to tell me it's normal, but there'll be 2 different possible answers as to why. The first one will be, well, because you told me the parent distribution was normal. And I know that anytime the parent distribution is normal, the sampling distribution is automatically normal. That's true. But sometimes I won't. What if this problem said the number of pepperonis on a pizza is right skewed with a mean of 16 and a standard deviation of 5? You might think that then you couldn't do the problem. But you could, as long as your value of n were large enough. Because if your value of n is large enough, then it doesn't matter what shape the parent distribution had. Right? I've shown you left skewed and symmetric so far, but I think this lets me, here, let me put up the weirdest looking distribution you've ever seen. Oh, sure, something like that. Oh, that's pretty weird. And I could certainly animate observations from there. I probably should have cleared it out first. A lot of them over here, but there's kind of some in here and some here. I could do that, and I can get averages. And you're like, no, this is the craziest looking parent distribution I've ever seen. There's no way the sampling distribution is going to look not. Oh, wow, look at that. Right? Because my sample size, it's 16 in this example, is large enough, it doesn't matter what my parent distribution looks like. My sampling distribution looks pretty good, pretty normal. And you can mess with this. You can make it whatever you want. Doesn't matter. You fill up everything. They have this thing called uniform, where the number of pepperonis on a pizza, it's just random. It could be anywhere from 0 to 32, and it's completely random. No idea how many pepperonis are on a pizza. They're all over the place. There's no rhyme or reason. Different pepperonis, different pizzas, different number of pepperonis. Do this a whole bunch of times, bam. There's your normal distribution. That's the central limit theorem in action. As long as n is large enough, doesn't matter what shape my parent distribution has, my sampling distribution will be approximately normal. You're like, I don't like that. I don't like you saying as long as n is large enough. Because that's confusing. What's large enough? Is 15 large enough? Is 10 large enough? I don't know. Why don't we, okay, so in reality, it's just if n is large enough. But for the purposes of our class, why don't we choose a value of n as this arbitrary cutoff and say that as long as n is bigger than this number, then we're always good. And that way there won't be any subjectivity to it. We can always agree. That's what every textbook does. And every textbook that I've seen uses the exact same number. They use 30 as the cutoff. That seems a little conservative. That seems like bigger than you'd need. They say that if the parent distribution is not approximately normal, the sampling distribution will be approximately normal as long as n is greater than or equal to 30. Note that that's probably more than what we need, right? I gave you some pretty weird looking distributions already and haven't had NB30. 16 looks pretty good. But maybe for the sake of maybe you could see a tiny little tail in here. Maybe for the sake of conservatism, we should make n even larger. The largest this applet will let me make it is 25. Let's call it 30. Let's say by the time n is 30, this is approximately normal and I'm good. The standard deviation down here is exactly 1. Whoa, weird. Where'd that come from? If you can explain or if you can understand why this is exactly 1, it's pretty good knowledge of what's going on here. The spread here, the population standard deviation of the sample averages is exactly 1. Why? Well, because we have a formula for it. Right? The formula for the population standard deviation of the sample averages is sigma divided by the square root of n. And if you go back to this applet, sigma has always been 5, the standard deviation of the parent distribution, and we just moved n up to 25. And the square root of 25 is 5, and 5 divided by 5 gives me that 1. If you're following that, that's really good. That's good knowledge of this stuff. One last comment I want to make. The last comment refers to this thing. This thing's a mouthful. I just said it a minute ago. It's the population standard deviation of the sample averages. There's no way. I'm not going to remember that. You really want me to remember that whole phrase? That's really annoying. Do statisticians really use that entire phrase? Do they really say it's the population standard deviation of the sample averages? The answer is no. I mean, some do. It's exactly what this means. You could say that. But a lot of people, because that's such a mouthful, just call this the standard error. Because if they call this the standard error, then they can call this the standard deviation and don't have to specify. It's the standard deviation of an individual observation, and this is the standard deviation of the sample averages. The population standard deviation of an individual observation, often they'll just say standard deviation. And so that you aren't confused when someone says standard deviation, this is commonly referred to as the standard error. That's a little bit about shape, center, and spread. We can now answer all of these questions. I know I've only done one question. I've made 3 videos. I'm going to add one more video in this section where we do a lot of questions. But I think what you'll see is I'm not teaching you anything new in this next video. We're just redoing what we learned in 3.1, just under the assumptions of these last 3 videos.